All right, we have another problem. So let's take a look. We know that the species will exist like this. We can identify our base as hydroxide and then our acid is the weakly acidic alcohol. I will take my arrows and I will draw it accordingly. Again, because oxygen is more electronegative than hydrogen, the bond snaps onto it. And what we see is that we form an alkoxide and water. And the question now is, what side will it favor? Remember, will it favor this base? Is this more stable or is this more stable? So the bases in question are our hydroxide and then our alkoxide. And let's go through these factors. And this problem is confusing because we think about our factors, electronegativity has finally failed us. We are comparing apples to apples, an oxygen to an oxygen. Nothing different about it. Size fails us again. There's nothing different about the element oxygen in the left and the right. There is no resonance in either of these species. The hybridization is also the same. They're both sp3 hybridized. That leaves us with induction. And so I kept kind of funneling this one off to the side. And it's not because it's not important. It's just because these factors are so powerful that when you have these factors involved, induction is typically not as significant. But in this situation, there's only one thing that dictates the difference between this basis stability and this basis stability. And the question is, how does induction do that? And I've kind of explained induction before. And induction is the nearby atom's affinity to either shove electron density at you or suck it away. And what I've gone over a couple recitations ago is that alkyl groups or alkane groups nearby are weakly electron donating. So the inductive effect of an alkyl group is actually to weakly donate in. And the difference between the hydroxide ion and this alkoxide is that the alkoxide has a neighboring carbon. And that carbon's natural tendency, this alkyl group's natural tendency, is to donate a little bit of its electron density. This hydroxide has no carbons next door that are going to donate it. And what we see is that this slight electron donation is adding fuel to the fire. Oxygen is able to stabilize this negative charge, but it doesn't want more. So when this alkyl group or adjacent alkane is donating more fuel to the fire or electronegativity to already charged species, negatively charged species, this is destabilizing. And what we see is that this is actually the more stable form. So when we're thinking about equilibrium, because of electron donating inductive effects, this is not as stable. So what we find out is that this base, hydroxide, is actually the more stable. And that's very counterintuitive, right? Because you think hydroxide, you think strong base, you think the end-all be-all of bases, but hydroxides aren't that strong. I mean, they're relatively strong. They're more common than they are really strong. And that's important to recognize, is that this alkoxide is actually more unstable or strong of a base than this hydroxide. And we think about pKa's, we're at 15, or I think this one's actually at comes in at 16, and this one's at 15.7. So I know alcohols come in at around a base value of 15, but because of this alkyl donation, it actually raises the pKa slightly. So it's a very subtle difference between pKa's, but we see that the equilibrium does lie to the left. Granted, at any time, both of these All four of these compounds exist in solution, but we have a slight bit more of the left side. And that's due to inductive effects destabilizing the resulting conjugate base. So I wanted to follow up that acid-base problem with this slide that shows what happens to the effect of acidity on alcohols as you add more alkyl groups to your molecule. And you can see on the way left, water is the most acidic. And the moment you start adding more adjacent alkyl groups or carbons nearby, you have a higher or a larger net dipole effect, which is donating electron density towards that O. And carbons have that natural tendency to donate electron density. It's just how they are. They are weakly electron donating. So if we're thinking in terms of stability in our conjugate bases at the bottom, having more alkyl groups nearby is more electron donation. And it's adding more fuel to the fire. The oxygen already has a negatively charged situation. Why would it want more electron density, more negative charge? That's the opposite of stabilizing, which stabilizing would be delocalizing that charge. But what we see here is carbon is just forcing a tiny bit of electron density onto that already negatively charged O. And that destabilizes the conjugate base. So you can see on the way right, T-butyl alcohol is the least acidic because it has all of this alkyl donation, which destabilizes the resulting conjugate base.